Now, we have seen what the second order circuits are already. Now, what we are going to do here, we are going to analyze a second order circuit. That means which includes one inductor and one capacitor in it. And it is a simple second order circuit. Just remind you where we are mathematically, because this is going to be a mathematical model. We already seen that for the resistive circuits, the mathematical model is a linear equation, set of linear equations in the form of Ix equal B. When the energy stored elements, L and C elements, are included in a circuit, then the mathematical model changes. It becomes ordinary differential equations. So in general, this ordinary differential equation is in this format. What we are seeing here, the derivative of the unknown, is seen in the equation. Also, the unknown itself is also seen in the equation. Therefore, it is called a differential equation. Now, in our case, since the second order circuit that we are dealing with, this differential equation is going to be a second order differential equation, or first order differential equations, but two of them together. What I mean is this, maybe it is better to show here. At the end, we are going to deal with a second order circuit like that in this chapter. So the mathematical model of this second order circuit could be either a second order ordinary differential equation like that, or another, this one, or this is the another mathematical model that we are dealing with. In this mathematical model, we are going to see only the first order derivative here. In the first one, we've got a second order derivative included in the equation. That's why it is called second order. But in this case, we've got first order differential equation in each equation, but there are two equations. In each equation, we have only first order derivative, not the second order. So this is the model that we're going to use in the circuit theory. There are some reasons behind it. I will explain it later on. Now, what we are saying, I'll come back to our frame here. So we are talking about this. So if it is second order, this is going to be a second order differential, second order ordinary differential equation. So the format is like that. So let's go inside this equation. If it were first order differential equation, the capital A became small a. You remember that? That small a was a constant if the circuit is the first order circuit. In here it is a matrix, that's why we show it as a capital letter, that A. A is a matrix. So this differential equation, this is matricial differential equation. We call this equation, we give a special name to this equation. It is called state equation. That is the mathematical model of a circuit in physical world. So what are the variables here? That T is independent variable. So independent variable, and N has been forgotten here. Let me correct it at the same time. Independent equation. In mathematics, this independent variable could be chosen as x, but in here it is different. We are choosing the independent variable time t. Unknowns. The unknowns are these are special. In our case here, the unknowns are the special unknowns. They are called state variables. State variables of a state equation, which is this x, is inductor current and capacitor voltage. You cannot change these state variables. So that means inductor current, I said, you cannot say inductor voltage cannot be a state variable. I said capacitor voltage, you cannot change it with the capacitor current. So state variable must be capacitor voltage, not the current. There are some reasons behind it. Maybe in order to help you to remember which one is the state variable directly related with the initial conditions included variables. For example, initial condition of an inductor is IL0, isn't it? So inductor current. Initial condition of a capacitor is VC0. That means capacitor voltage is the state variable. What is the coefficient? So the coefficient is going to be A matrix, we said. Inside of this A matrix, we've got the element parameters that we see in their definition relations. So for example, a simple circuit that we are going to examine here is going to be this one. So in the A matrices, what we are going to see here, V, R, C, and R. These are the parameters that we see in the definition relation of these elements. So what we are going to see in A is this, and we said A is a square matrix. B is a column matrix. What is inside B? Inside B we've got once again element parameters included here, but the difference between capital A and capital B is that the A is a square matrix, B is a column matrix. What is UT? UT is the known in mathematics. This what is known in mathematics, they call it a function which is given to you. Function of t, for example. Any function is UT, could be a UT, but in physical world that UT is independent sources related variable. If it is independent voltage source, it is the independent voltage source voltage. If it is independent, if there is independent current source in your circuit, independent current source current seen as UT in our equations. So let's explain the last sentences here. That's important. Once the state variables are found, then all the elements current and voltages will be found. So in here, when you solve these differential equations, you're going to find out inductor current and capacitor voltage. It is said here that once you found that inductor current and capacitor voltage, you can calculate all the elements current and voltages. So it is similar saying that if you use the mesh current method, once you calculate the mesh currents, then you can find all the elements current and voltages. If you are using node voltage method, you're going to find out all the node voltages. Once you found all the node voltages, you can find all the elements current and voltages. So that's similar to this one. In here we are saying if you find the state variables, in our case second order, inductor current, capacitor voltage, then you can calculate all the other elements current and voltages. So we said what the mathematical model is. The next step is how we are going to find this mathematical model. So we've got to give an explanation here. So the examples that we are dealing with in this circuit theory course is the first order and second order circuits. These are simple circuits. But in practice, we might have a more complex circuits. We are not examining here because in order to examine those, we need to use graph theory. Graph theory is not part of this course. Why it is not part of this course? Because Proteus similar simulation tools use the graph theory behind in order to find the differential equations or state equations that we needed to analyze the circuit. So for complex circuits, the basic idea does not change, but the calculation is a bit boring if you are doing it by hand. But for the complex circuits, you do not need to do it by hand. You can use the Proteus as a simulation program, and you can find all the elements, current and voltages. So if we go back now, saying that the format is going to be the same, so the calculation or calculation time becomes a bit longer. We don't want to waste that time for doing it by hand, but we need to do it for small circuits to see that format. That's why we are examining it here. So the simple second order circuit that we are going to examine is this one. There were two of them, but we are going to use this one. So parallel RLC circuit analysis. In this parallel circuit, we've got one inductor and one capacitor. Therefore, we've got two energy stored elements in it. It is a second order circuit. So how we are going to find the state equation for this circuit? As we said already, since this is second order, so we are going to find a differential equation in this format. What we are saying here, as we said before, the state variables are inductor current and capacitor voltage. These are the state variable. In here, this is the state variables derivative of it. This is A matrix for this second order circuit, and this one is the B matrix as is shown here. A matrix, B matrix. These are state variables, VCT, ILT, and the state variable derivative, dVC, dt, dIL over dt is the derivative. So how we are going to do it? So do it step by step. So I'm going to switch to board video now. So okay, this is the second order circuit, so we're going to find the differential equation. So what we are going to find, I will write it here. X derivative is equal A times xt, forget that t, so our independent variable t, plus b ut. So remind you now, what is x? T, there are two of them. One of them is inductor current and the other one is capacitor voltage. That is xt. A has got, is going to, what we are going to see in A is going to be a square matrix. The dimension is 2 times 2 because it is second order. And what we are going to see inside are LC values. And for B as well. So I know what I am going to end up with. So we said how we are going to write this equation. As we said before, we are going to, since it is a simple function, simple circuit, simple second order circuit, we will be using the Kirchhoff current law, independent current law equation, Kirchhoff voltage law equations, independent ones, and the definition relation. So let me write all that. In order to write that, we need to put references for that. I have chosen the reference, current references downwards. So there are two nodes. One of them is the ground, so that's ground. And I'm going to write Kirchhoff current law equation for this node, just one of them. So let me write it. IL plus IC plus IR. All the sign for all of those three is plus. Why is that? Because all of them coming out of the node. So the independent current source current towards the node is going to be minus on the left hand side. If I move it on the right hand side, it's going to be IT. So capital IT it says there. This is Kirchhoff current law equation. What about voltage law? Kirchhoff voltage law equations for this circuit. Since all these elements are connected in parallel, we know that parallel elements voltages are equal to each other. This is written by using Kirchhoff voltage law equations. So we're going to write 3 equations. From these 3 equations, we are going to end up with VC equal VR equal VL. Inductor voltage, resistor voltage, and the capacitor voltages are equal to each other. So you can check this. You can write, for example, for this mesh, if you write the Kirchhoff voltage law equations, you're going to end up with VL equal to VC. VL equal to VC. That's the one. So we finished this one as well. What is left? The definition relation. So definition relation, by definition, this is known, isn't it? So this UT, maybe I should have written that when I have it right here. So that UT here, independent voltage source, current source, current. So that's the one. So I'm not going to write the definition relation of this, any function it could be. So come back to here now. Definition relation for the other elements are going to be, for the capacitor, it's going to be IC equals C times dVC over dt. This is capacitor definition relation. And VL equal L times DIL over dt. This is inductor definition relation. And the resistor definition relation, VR R times IR. So this is the equations that I am going to use. That's why I am saying that we do not need to use the graph theory if the number of elements are limited, as we see here in this second order circuit. So since I know this, I am looking for an equation in which I am going to say the derivative of VC over IL, and all the variables that I am going to see is going to be the state variables. These are the ILT, VCT. And then I know that in the equation I must see also this UT. UT is IT. So if you look at these equations that I am going to use, just one of them has got that IT in it. So I need to use this equation, because in the other ones, you see, there is no IT. But I know the equation that I'm going to find, there must be IT. That is UT in mathematics and IT in physical world. So I need to use this equation. So I will be writing this equation once more here. IL plus IC plus IR is equal IT. So this IL here is the variable that I needed, isn't it? Because ILT is my state variable. So I am going to keep this as it is here. IC is not the variable that I am looking for. This is not a state variable. How I can transfer this variable to a state variable? You could easily see that if you use the definition relation, you could do so. Because IC is transferred to VC if you use this definition relation. So if I write here C times dVC over dt. So this is the state variable, so I accept that. And IR is not a state variable, so I would like to get rid of it from that. So if I use the definition relation, it's going to be VR over R. But on the other hand, so I need these state variables. I can transfer that VR to VC, because VR equal to VC. VC is the state variable. So this is what I need. If I transfer this now, this is a equation that I need, because in here I have got the derivative of the state variables and also state variables itself. in the equation. So it is in this format. So if I write this separately and keep the left hand side is just the derivative of the state variable, so you're going to left hand side is going to be this one. So I'm going to divide all the others by c. So it's going to be dvc over dt is equal minus 1 over c il t. And if I move this one on the right hand side, minus 1 over rc vc plus 1 over c it. So this equation now is in the same format that I needed to put in. Derivative of one of the state variable equal state variables. There is no any other variable included in this circuit. All state variables are seen here. So that X is that is. And this independent current source current function is here. So this is the format that I am looking for. But this is only one equation. I've got to find the other equation. In the other equation, I'm going to see the derivative of the other state variable. That means dIL over dt I would like to see. So where I see that derivative in the definition relation of this inductor here, I could see that. So if I write this equal to 1 over L VL. On the other hand, I know that VL is equal VC. Here you are. Then it becomes VC. Then I can say that I can write this in this format, dIL over dt is equal 1 over C. No, this is L, isn't it? I made a mistake, sorry. So, okay. So that is L. Definition relation I see L. So 1 over L. VL equal VC, so it's going to be VC. So in this case, this is 1 over L VC. So I am saying these two now. Let me write these two differential equation in the matrix form. So it's going to be like that: dVC over dt, dIL over dt. So I will be writing this A square matrix. The dimension is going to be 2 times 2, and then IL VC, maybe write T as well. And B column matrix and IT. So this is going to be A matrix, A column matrix, and that is B. Dimension is 2 times 2, dimension is 2 times 1. So what is this coefficient? Is the coefficient of ILT. Coefficient of ILT here is minus 1 over C. Coefficient of VC is minus 1 over RC. And coefficient of IT is 1 over C. So I transfer the first equation to this matrix form. So the second one, ILT coefficient, since it is not seen in this equation, is going to be 0. VC coefficient is 1 over L because of that. And since we don't see the IT in this second equation, I'm going to put 0 here. So that's the differential equation, which is called state equation for this second order circuit. So this is mathematical model model. We can say this is state equation for this circuit. Now we are saying if we calculate this by solving this equation, so this is another step. We are going to calculate inductor current, capacitor voltage. Once we calculated those two state variables, we could calculate all the elements current and voltages for the given circuit. That means you can finish the analysis in the second step. Okay, you need 2 steps to do the total analysis. So let's come back to Prezi again. Okay, this one. So we found this, you see. So all this calculation has been shown as I have done it on the whiteboard in class, so we repeated it. So there is a comparison here between the circuit theory usage of differential equations and the mathematical usage of differential equations. It was possible to represent this mathematical form differential equation. What is this form? Only the first order derivatives seen in the equations, and there are 2 equations here. Total 2 equations. In each equation, only the derivative, first order derivative of the state variable is seen, not the second order. So the alternative to this one, mathematically, you could say that you can transfer those 2 equations to just one equation in which their second order differential equations included it and only one variable included it. So if you look at a similar way, if you consider it, you are doing the variable elimination. And then instead of 2 equations, you can make just one equation. And in this equation, only one variable seen. So that in this now, there is one state variable, but this state variable's second derivative is also seen in the equation. So the solution of this in here mathematically is going to be the same solution that you're going to find here. You might have seen in differential equation course this second order differential equation, just one. But in circuit theory, we will be using this type of format. There are some reasons behind it. I will explain that later on. In the calculation of some of the parameters, in this format is easy. In this format, it takes time. That's why we will be using this one. So that is the end of this video then. So let me stop here.